Hello, everyone. If you're here to learn about Graviton, you're in the right place. So today I wanted to share with you a story of how we at Honeycomb managed to do a large-scale migration while all of the data was in flight over to Graviton 100%. And this doesn't just apply to Graviton. This is something that you can apply to any kind of migration, although we think that Graviton is great. So imagine that it's the middle of the night, and you're having a great, peaceful night of sleep, and suddenly your pager does this. How do you feel? Do you feel confident? Do you feel scared? Or do you feel that you have no idea what's about to happen? So my company enables software developers to get a better sense of what's going on inside of their systems using big data. And we believe very strongly that it's not just about storing the data, it's also about giving you those insights as quickly as possible. So when we want to get those insights as quickly as possible, we're willing to spend quite a bit of money to make sure that the developers who are trusting in Honeycomb are able to get that insight and get back to sleep as soon as possible. So in that spirit, we very strongly believe that we want to maintain a service level objective of 99.5% of queries that come into Honeycomb being returned in less than 10 seconds. So performance has always been really, really important to us. So we also think that it should be possible to add data easily, so that even if your system is scaling out, even if you're adding more and more important things that you care about, maybe it's build ID one day, maybe it's language pack, maybe it's which web browser someone's using, that those should all be things that you should be able to understand without having to pre-aggregate them in advance, without having to think about, do I need a custom metric for this? Or can I just go ahead and throw it all together into one single data store? So by giving people this insight, we're able to very rapidly help people with their production problems so that you spend less time doing break fix. So this is kind of the broader context in which we adopted AWS Graviton. And our customers find that this is something that they really value, is the fact that we're able to keep the prices at something that they can afford and give them really fast insight. So under the hood, we are a pure AWS shop, and we're ingesting signals both from AWS as well as from people's applications, and we're storing it with a custom columnar data storage format. So what does this actually look like in terms of the AWS services under the hood? Well, you might think, we've scaled by a factor of 20. Surely our cost has gone up by a factor of 20 over the past 5 years. And that's simply not the case because we've been able to benefit from AWS Graviton. So 5 years ago, we were serving about 300,000 trace spans per second. And now we're serving just about 5.5 million trace spans per second at peak. And 5 years ago, every week, we were serving 100,000 queries from Honeycomb users pressing the Run Query button. And today, we're serving something like 2 million queries being run against Honeycomb every single week. So this is the story of how we managed to grow the service without falling over and by making it even more efficient as we went along. So hi, I'm Liz Fong-Jones. I'm the field CTO at Honeycomb, and I'm also an AWS community hero, and I cover the Graviton focus area. So what are we going to talk about today? Well, first of all, we talked about kind of what's the context, because some of the things that we do might be only applicable to us, but some of the things might be broadly applicable to you. So I feel it's really important to focus first on what are you trying to accomplish, what's the goal, and then how can cost optimization fit in. Over the next hour, we're also going to be talking about the context in which ARM64 came to be such a powerful force. You heard it in the keynote on Monday, right? Over 50% of new CPU deliveries coming into AWS are Graviton today. But where did that all come from? How did we get to this point? And then how did Honeycomb actually carry out our migration? What did we consider? How did we actually design our experiments? And how did our rollout actually go across all of the AWS services that we use? So let's roll the clock back 40 years. Let's talk about what happened in the 1980s. So in the 80s, in the 60s, 70s, 80s, right, you had mainframes. And each mainframe had its own bespoke architecture. And programmers had to develop their code specifically for that specific mainframe. And if you had to port your code, good luck with that. That was going to take a long time. But software was very expensive to write back in that day, so it was OK. But then came the age of desktop computing. And we can kind of think about this primarily in the context of Intel versus Mac, x86 versus Motorola 68K. Again, bespoke operating systems, people were writing their software primarily for one or the other with very expensive porting processes. And yes, there is a brief flourishing of kind of the mini frames or workstations, but in reality, most software developers were developing their software for x86 or 68K. The world went 64-bit, so people had to port their architectures again if they were porting to Itanium, and that's why that really failed, right? Like, people really had a lot of inertia around wanting to keep their software exactly the same, to run it against the same architecture and just have that binary that you built 20 years ago run the same as it does today. So that's why x86-64 won at that time, was that it was backwards compatible with x86. But in parallel, what was happening, unbeknownst to many people who are doing server development, who are doing data center development, was the mobile revolution. That ARM32 chips came into play across all of our cell phones, all of our mobile devices, because they were so power efficient, and people were willing to make those sacrifices to change over to a new architecture in order to avail themselves of this new delivery mechanism. But there's been so much inertia behind x86, so it had to be a good enough change. It had to be a powerful enough change to get people to really think about how might we change the way that we deliver software in the data center. So today, there's a robust ecosystem of not just x86-64, but also ARM64 and RISC-V processors that are competing for the future vision of how should we deploy software in the cloud. So with that in mind, the thing that made it possible was both an improvement to price performance and also the availability of open source delivery systems. In the past, if you wanted to get support for your software to run on ARM, you had to have the operating system maker support your new architecture. You had to make sure that all of your supporting libraries, maybe all of those proprietary dependencies that someone wrote 20 years ago, you had to port those to run on that architecture too. But what changed was that Linux and the open source ecosystem became the predominant way that we ship software, that we are starting to ship software on top of containers. We are starting to ship software on top of Red Hat or Ubuntu, and therefore, those open source operating systems were now a suitable platform where those could change and you could recompile your code and you were not dependent upon someone else having to change their code over to support the new architecture. So with the advantages of better cost, we were able to finally get that business case in addition to having it be easier to swap over. So fundamentally, why is ARM more efficient? Why is it that you can get such improved price performance out of ARM? As you may know, the vCPU construct inside of AWS, right? Like when you are buying a vCPU, you're buying half of an actual core of an x86 machine. And that's because the x86 instruction set is about 40 years old, right? Like there is so much of this instruction set that was designed around the idea of creating more and more and more complex instructions that you could instruct the chip to do. And therefore, the instruction sets got larger and larger. How many of you have seen the Intel x86-64 programming manual, the book of all the assembly instructions? Okay, there are two or three nerds here in the audience, but it's as big as a phone book, and it's getting bigger every year, right? So there also has to be a large area of the chip that's devoted to decoding those instructions and making them ready for execution by the more modern cores under the hood. In contrast, ARM does not have this idea of a vCPU. One core is one vCPU, right? Like it's one execution unit. You don't have a separate doubling up of your decode units versus your execution units. And that means that you can execute your workload, right? Like for the same number of vCPU, you can execute it twice as fast because you're not contending with your own workload. You don't have the situation of, two things that have both decoded and are both waiting on that same ALU. So therefore, you're able to push the system much harder and not see any degradation in your latency. And also, using the latest process node, because a lot of the work going on with ARM and the Neoverse cores has been really optimized to run on the latest process nodes and manufactured using the latest, using the smallest transistors, so it's able to run a lot more efficiently. So that's how Amazon is able to offer lower prices to those of us who are consuming. So this is what our Graviton journey looked like at Honeycomb. reInvent 5 years ago was when Graviton 2 was announced. And we saw this, and we thought, hey, this seems really cool. Getting better cost, better performance, and also improving the amount of impact that we have on the environment, that seems like something that's great, right? Like, we're willing to try some things out. We're always a believer in doing the bleeding edge things at Honeycomb. So before we embarked upon this project, I had to sell my organization on, right, like, OK, great, there are all of these potential benefits. What about the potential risks, right? Like, how can we mitigate the risks in doing a pilot of a large-scale migration of our software? So we had to think first about how are we going to defend the user experience first and foremost. So as I mentioned before, we aim to return 99.5% of queries within 10 seconds. We aim to ingest 99.99% of data the first time around without you having to retry, right? Like, those are things that we view as pretty immutable. So we wanted to make sure that we had safeguards to stop deployment of the new Graviton experiment if we detected there was going to be some kind of performance degradation or problem. So by putting guardrails in place, by defining these are thresholds under which we'll continue the experiment, these are the thresholds under which we'll stop the experiment, that gave my leadership team confidence that this was something that was not going to break our system. So the cost argument was obviously something that we considered a lot. And at the end of the day, because we are a software as a service business, we care very much about our cost of goods sold. We care about our efficiency as a business. For every dollar that our customers pay Honeycomb, we want to make sure that we're not spending too much of that money on the cost of providing our service. And infrastructure, our AWS bill, is essentially our #2 expense after paying for our people. So therefore, it was pretty compelling to the finance team to say, you know, OK, great, we're going to try this Graviton thing, and if it works, we're going to have a lot leaner of an infrastructure. But the other thing that's kind of a little bit more hidden, it's not just performance, it's not just cost. There's also the amount of bandwidth that it takes from our people. We had to really think carefully about, does my team have the bandwidth to work on this project? Are we going to be willing to support this on a long-term basis? Right? And at the time, it wasn't 100% clear yet whether ARM was going to be the market leader. So we wanted to know, right, like, are we going to converge in one architecture at a time, over time, or are we going to stay multi-arch forever? We wanted to make sure that our software developers could have a predictable experience with, if the code ran and the test passed, that it would run successfully in production. So we had to really think carefully about what was going to be our criterion for kind of converging on one architecture rather than kind of maintaining two separate architectures over time that might diverge or drift. So once we'd made that initial case and kind of set up the parameters of the experiment, we had to think about how to concretely port our software to run on Graviton. So that fell into my lap as the person who advocated for the project. So what we needed to do was we needed to fundamentally produce a build artifact that was built for the ARM architecture. So this requires you to have a suitable base to run on, whether you're using Docker images, whether you're using EKS, right? Like, you have to make sure that you have the right AMIs. You have to make sure that you have all of the stuff that your software needs to run, all of the base layers underneath it, that they're compatible with ARM. We had to go through our application code and make sure that it would build successfully on the new architecture. And then we had to tool our CI tooling. We had to change our CI tooling in order to produce different build artifacts. Because in a majority of cases, you cannot necessarily just take your build artifact that runs on x86 and just run it directly on ARM, right? Like, if you try to pass the wrong architecture of Docker image to your kubelet, it's not going to start it. It's going to say, you know, architecture exception, right? So we had to go ahead and do that work. But fortunately for us, we use the Go programming language. And the advantage of the Go programming language is that it was built out of the box to support running on multiple operating systems and architectures. So by just setting one environment variable, by just setting the GoArch environment variable, we're able to make build artifacts, or binaries at least, that ran on the ARM architecture as opposed to the x86 architecture. If we'd been using Java or Python, it might have been even easier, because in those cases, unless you're using a native extension underneath your jars or inside of your Python using CPython, right? Like, you're probably just executing against the runtime. And if the runtime is part of your operating system, then you might be good to go right off the bat. We might not have done this project if we were a pure C++ base, simply because C++ has a lot of potential for you to do architecture-specific things that we'd have to ferret out. There was one caution that we ran into, though, which is that when it came time to build Docker images, if you were trying to build Docker images on a non-native architecture, so if you're trying to build an ARM artifact on an x86 machine, you have to use QEMU in order to do the Docker build steps, and that can be a little bit slow. So, but the good news is since 2020, things have gotten a lot more widely supported such that you can find ARM workers on your platform of choice, whether it be GitHub Actions or Circle CI or BuildKite. So once we had the build artifacts built, once we had the base operating system layer put together, we could then start doing A/B testing. Now, here are some of the things that we found while doing A/B testing. We wanted to make sure that we were doing an apples-to-apples comparison, and we wanted to make sure that we were sending realistic traffic streams in order to simulate the behavior. And we wanted to make sure that we were validating the claims that the Graviton team was making at the time, that the M6G instance types were going to be about 20 to 30% better on price performance. So in order to test that, we just booted up some machines on the ARM architecture that were powered by Graviton 2, and we forked a certain percentage of our traffic over, and we sent 20% of traffic over to those new instances, and we went to see how they would perform. Now, let's talk about performance goals, right? Like, what were we looking for? Well, the first thing we were looking for was, does this even work correctly, right? Like, if it doesn't return correct results, that's a problem. The good news is that it did return correct results. But the other factors were, right, like, what should I expect, right? Like, do I have adequate observability to understand what's going on? Right, so in this specific case, we were looking to see, okay, does the latency of the requests that are flowing through, is that getting shorter? Are we able to slam more throughput per machine? If it breaks and starts serving errors or starts getting really slow, how will we know? And also, we wanted to understand things like, can we take away machines, right? Like, sure, right? Like, does it actually matter if each request is 100 milliseconds faster if we're still spending the same amount of money? Right? So we wanted to see how hard we could actually push this. And also, because I come from a reliability background, I'm going to emphasize hidden risks, right? Like, there are a lot of things that can potentially go wrong, so we had to consider in advance, even if the experiment was going to go well, we wanted to think about the worst case, right? How am I going to roll this back, right? How quickly can I hit the stop button on this experiment? How do we know that our developers are trained and enabled on this, right? What happens if something works on x86 and doesn't work on ARM, right? Like, who's going to debug that problem in the build? Who's going to make the build turn green again? And we had to work with our vendors because in some cases we were using proprietary software, and we wanted to make sure that we could bring that along for the ride. And those are things that were not necessarily inventoried at the start of the experiment, but were things that we wanted to make sure that we'd allowed some room for. Also, we did have a few breakages in the process. I'll talk about them a little bit later, but we did have some things that went a little bit sideways, and we had to make sure that every time we had a change that didn't go exactly according to plan, that we backed off from doing that change for a little while, gave people time to recover, rather than saying, we're just going to slam this change through, and the pager's just going to keep on going off, and that's fine, right? Like, we wanted to instead make sure that we're running our systems in a stable state, not a metastable state. Metastable systems are the worst because as soon as they get slightly out of whack, suddenly you have a hard time restoring them back to normal. So we spent a lot of time testing and validating before we moved out to production because we wanted to make sure that we were fully accounting for the impact of everything. So when you're thinking about doing a large-scale migration, it's super important to think about, how are we going to actually finish this program, right? If I get 99% of the way there and there's just 1% hanging out there, right, what's the factor that actually forces us to finish that migration, to clear that technical debt off of our backlog so that we're only maintaining one architecture going forward? So let's talk about that rollout strategy. So we did the Graviton 2 evaluation in early 2020. And we needed to pick a place to run it. So we could have said, look, so I and my boss, Charity Majors, are pretty famous for this idea of testing in production. And yes, we believe everyone tests in production, whether you like it or not, whether you're in denial about it or not. But also, that's not saying don't test in staging. So we do have a staging environment, and that staging environment is called dog food. So we use Honeycomb every day to understand Honeycomb. So instead of pushing Graviton straight out to our production cluster, we push Graviton out to our dog food cluster, which is about a fifth the size of our production cluster, so it still is a sizable volume, and it's something that if it breaks, only our own employees are impacted and not everyone else. So that's where we pushed out the experiment. And then we used another environment called Kibble, which observes dog food, Because it's a little bit of an Ouroboros, right? Like we use our own software to observe itself, observing itself, to make sure that we are always having the right controllability and observability. So in terms of our service architecture, we needed to also think about, OK, we've picked to do this experiment in the dog food environment. Where should we insert this into our architecture? So in general, we've got a number of stateful components, and we've got a number of stateless components. So we wanted to really pick something for this initial experiment that we could easily roll back, that was not, in the event that it corrupted data, that it was only going to impact a small subset of the data, and that we wouldn't have to replay a bunch of data to restore it. So we picked that data ingest worker that receives OpenTelemetry formatted observability data. We picked that to experiment with because it was a stateless service that we already had made sure was something that could survive rolling restarts, that was persisting data to Kafka, and therefore it itself was not holding on to the data for very long. It also is our highest traffic service in terms of number of queries per second. And also, it scales very cleanly. The only scaling dimension that it cares about is CPU utilization, because of the fact that it is essentially ingesting protobufs and outputting protobufs over into Kafka, right? Like it's doing the validation and transformation, but it's not actually holding on to the data. So our initial findings in 2020, after we did our test deployment, was that we were able to get about 20% better performance, and also that each core was going to cost us, each vCPU was going to cost us 10% less. But we needed to actually get a little bit better than that, right? Like, sure, each core performs 20% better, but how do we actually know that, right? Like, so we actually took away cores. So the fascinating thing that I mentioned earlier about CISC x86 instruction sets is that because you have 2 decode units for every execution unit, if you really cannot saturate an x86 system that is running a single workload larger than about 50 or 60% CPU utilization. So if you trial ARM and you run at 50 to 60% CPU utilization, you're not necessarily going to see the full benefit. We actually, because we had our service level objectives, this is the performance target that we're trying to hit, we actually went ahead and said, OK, what if we take away instances? What if we start running at 60%, 70%, 80% utilization targets? And we found that the Graviton 2 instances did not degrade on their latency, even when we ran them 20% hotter than the x86 instances. So that's where a good portion of that cost savings comes from. It's not just the cheaper per core. It's also the aspect of being able to use fewer cores. And if you do not actually stress your system and run it until the latency starts to degrade, then you're going to look at this and be like, oh, this is a little bit underwhelming. And that's because you are assuming that x86 and ARM are behaving exactly identical, that you can only saturate it to 50 or 60%. So the porting of the code was super easy, right? We set a single environment variable, we changed our CI, we were done, right? Like, that took a few afternoons, but actually rolling it out through our fleet, that was a much more involved process. But when we actually did it, this is what we found. We found that the median latency got about 10% better, but the tail latency got substantially better, something like 20 or 30% better. So we rolled this out to our dog food environment, and we saw the costs immediately drop. And then we rolled it out to the production environment, and we also saw our costs immediately drop. And the other weird, interesting thing here is we were using spot instances, x86 spot instances before. And it turns out that on-demand Graviton instances actually outperform spot x86 instances for cost. And there also are offerings of spot for Graviton as well today. So this was all on not bare metal, but on raw EC2 instances. But in 2023, we migrated to Kubernetes and began using EKS. And of course, Graviton is fully supported on EKS. So when we did this migration, we switched over from deploying just zipped binaries, and we switched over to containers. And we were using cluster autoscaler. So we do not use Carpenter in our setup. This is a peculiarity of us. This may or may not apply to you. But we find that homogeneity in our Kubernetes cluster really, really matters to us. Why is that? Well, every generation of Graviton seems to get something like 30% better performance per core. So you can imagine that if you're setting your targets for amount of limits and requests of your CPU on your Kubernetes workloads, but some of the cores run 30% slower, or some of the cores run even, heaven forbid, 50% slower because you're running something that's 2 generations old, right? That's going to really, really mess with your auto-scaling. So we find that we have the best experience when we just limit our clusters to using a specific generation. So we did our migration, right, like entirely from x86 to Graviton 2. Then we did our migration exclusively from Graviton 2 to Graviton 3, and from Graviton 3 to Graviton 4. But we really do not like mixing those generations of Graviton because of the fact that the slower instances will fall behind, and they'll have a larger and larger backlog of traffic until they fall over. So using cluster autoscaler and just using the same consistent generation of instances has been more helpful to us than using Carpenter to kind of optimize spot and optimize whatever's the lowest cost, because we care about predictability, not just cost. So I think 2 years ago is when Graviton 3 became a GA roughly, and because we had invested the effort in porting from x86 to Graviton 2, we got all of the performance benefits from Graviton 3 essentially for free. We just changed that C6G to C7G, right? Like we're able to just increment the generation number, and we immediately saw improved throughput for that shepherd, for that ingest worker. So we're able to serve more traffic out of the same number of cores, and also with a lower latency, even when you accounted for taking away the cores. So we, of course, measure that, and we want to make sure that we are understanding, OK, right, like what's the ratio of previous versus current generation Gravitons that we're running, so that we can adjust the parameters of the experiment and kind of roll forward as quickly as possible if the experiment is successful because of what I just described of the challenges of running a disparate configuration of Graviton 3 versus Graviton 4 or Graviton 2 versus Graviton 3. So we do our generation upgrades via infrastructure as code. So it really is as easy as replacing a single digit, at least as far as writing the code is concerned. But obviously, there's a lot of this kind of performance engineering and actually battle testing it before we actually feel confident promoting that change throughout our environments. So yes, we did have to abandon Spot. And I think that this is one of the challenges that AWS is addressing. So again, right, like, I do not work for AWS. This is my real experience as a customer. We have a joke at Honeycomb about being gentrified out of our own Gravitons, right? So you may have seen Graviton 4 release, and you might think, great, like, no one's using Graviton 4. I have perfect availability of Spot. Let's just use Spot everywhere. So we had that experience with Graviton 3, right? Like we thought Graviton 3 is great, Spot is great. Let's try those two things together when we were migrating off of Graviton 2. But we very quickly discovered that the Spot pools, as soon as people also discovered how easy it was to increment that one digit in their configs, that suddenly all of those Graviton 3 instances that we were using suddenly vanished from the Spot pool because they were needed for production usage, right? Like for on-demand usage. So at this point, what we've realized is that kind of because we're seeing this predictable about 30% better price performance for each generation, it just makes better sense for us to reserve or get on-demand instances of the most current generation rather than potentially have to fall back on the previous generation when we're using Spot instances. So Graviton 4 for us, which came out recently, is about 30% faster than Graviton 3 for our workload. Again, your own mileage for it may vary. But I think one of the most powerful things about what AWS is doing with designing the Graviton chips is they're not just taking the Neoverse stock core design and applying it inside of AWS. They're also using data from real AWS customers about like what kinds of instructions do AWS customers execute. And then they'll design the chip in order to account for what are the most common patterns that AWS customers actually encounter. So our experience has been that we keep consistently seeing performance increases. And those are not necessarily things that you would see out of a benchmark, because we're not just running a benchmark, right? Like we're processing real protobufs that people are sending us. And our experience has been that we're just able to take away instances out of our workload every single time that we upgrade generations. So if you look at basically, this is comparing last year versus this year. So this is comparing our experience with running on Graviton 3 in November of 2023 versus running on Graviton 4 in November of 2024. So last year around this time, we were using something like 60 instances of M7G 8X large. And we were switching over. So this year, we were running about 100 instances of M8G 8X large, but we're serving twice the traffic as last year. So we're using about 50% more instances, but we're serving twice the traffic, right? Like I think that's a pretty good price-performance trade-off, even when you account for the fact that Graviton 4 per vCPU hour is about 10% more expensive than Graviton 3. So I think if you do the math, that's something like twice the traffic, 50% more instances, 10% more cost per instance. I think that pretty nicely squares with the AWS figure that they give you of 30% better price performance per generation. So today we're using EKS as our primary workload for scale-out workloads, and we're using M8G instances. But there are lots of things that are not scale-out workloads. And I did tease you at the beginning that we are 100% Graviton. So how do we migrate everything else? Well, it turns out that for RDS and OpenSearch service and basically any kind of service where you're telling AWS what virtual machine type to use, it's just a matter of changing over maybe M5 or M6i to M6G or M7G, right? So it's just a matter of changing that digit. Of course, you should do your own performance comparisons, right? Of course, you should do your own validation of workload. But we found that it was relatively easy just to flip that bit, have AWS replace our instances, and we're off to the races. So that's how we got some free performance wins, because in our case, at least, we're not running many different RDS databases. We have one big RDS instance that we use to store the metadata about the data that customers are sending us. So that really only scales in terms of, do you have a 4x large or 8x large? So by migrating from an M5 database instance to an M6G database instance, we avoided essentially having to double the size of that instance for a lot longer than if we had stayed on the previous generation Intel. So those are the easy ones, but let's talk about the hard stuff. Let's talk about stateful workloads where you have to preserve that data on disk. Let's talk about stateful workloads where you're maybe needing even the performance of raw NVMe rather than using EBS. So our Kafka brokers run IM4GN. I did see the announcement about I8G. We have not yet had a chance to try it yet. So we're using IM4GN. And we're also tiering data to AWS S3. So let's talk about the evolution of our Kafka cluster and how we evolved that to run 100% on Graviton at substantially better price performance. So winding the clock back to 2020, we were using i3 EN instances. And the i3 EN instances we were using were actually really, really undersaturated on CPU. We were a storage-bound workload because we wanted kind of to have a disaster recovery net, right? We wanted to make sure that we were keeping 48 hours of our customers' data stored on our Kafka brokers in case we needed to replay it. So we had to run more and more and more Kafka nodes. We were running something like, at the end, we were running 30 different worker nodes that were just occupying that disk and not doing very much else. So with the help and partnership of the folks at Confluent, we were able to migrate to substantially fewer i3 EN Intel-based local SSD nodes because we were storing everything older than 2 hours onto S3 and replaying it on demand, and only keeping the most recent 2 hours on disk, which meant that we had flipped from being a storage-bound workload to being a CPU and IOPS-bound workload. But at a certain point, the only thing left in our serverful infrastructure that was running Intel was our Kafka brokers. And we looked at this and we thought, why is it that we're maintaining two architectures? Why can we not simplify this to one architecture? So we briefly tried using C6GN instances and EBS, because there was not at the time a SSD variant, a heavy storage variant of the Graviton instances. So we tried using a non-storage specialized Graviton instance, and we found that we got into that metastable state I was talking about, where we were bursting above our CPU limits, we were bursting above our network limits, we were bursting above our EBS IOPS limits. And the system would work great until suddenly we got clamped down, and then we were in a state where it was really difficult to recover. So we said, OK, we're going to keep that in Intel for now. We need to back off the experiment. Let's wait until there's actually a proper replacement for i3 EN. So IM4GN came along, again, about 3 years ago or so. And we were able to migrate seamlessly, replacing our Kafka brokers just one for one from i3 EN to IM4GN. And this actually did not go perfectly smoothly. Sure, it ran initially out of the box, but we saw some performance problems that caused us to have to rethink how we were doing this. In particular, it turns out that when you're doing a lot of reading and writing to and from S3, because of that tiering that I was mentioning, so that we were no longer storage bound, the process of doing the cryptography transactions to do HTTPS requests to the S3 endpoint, that was sucking up a lot of time on our Kafka brokers. We were spending something like 20 or 30% of time on our Kafka brokers, inside of the MD5, or I think SHA-1 hashing algorithm. So we had to work with the Amazon Corretto team and with the Confluent Kafka team to figure out, okay, like, how do we make this dependency better? And it turns out that the default out-of-the-box libraries that were being shipped with Confluent Kafka did not include ARM support, right? Like, this is a situation where it turns out there are architecture-specific hand assembly optimized things or C++ artifacts that have been compiled into the jars. So we needed to replace that with something that was Graviton optimized. And after that, we were able to get much better price performance, and we were able to move forward with that rollout. Let's talk about our other stateful workloads. So we have this indexing engine, which is super, super powerful, right? Like, we ingest all this data from our customers, and then we store it broken down by column, broken down by which specific field is in each of these traces, in these traces. So this workload is something that is run with the data living on local SSD. And we were using originally, I think, i3 instances for this. And back in 2020, 2021, we were looking at this and we were saying, like, what if we could make that Graviton too? So we found that we were able to migrate over from i3 instances to M6GD instances. And the M6GD instances actually did cost more than the comparable i3 instances that we were using to get the same amount of local SSD. But we got 2 times as many cores for the same price, and we got 50% more performance per core. So paying 10% more for 3 times the performance was well worth it, because that enabled us to stop burning that SLO of the performance degrading. And we were able to scale by essentially a factor of 1.5 or 2 without adding more nodes, without having the latency degrade. And that bought us a lot of headroom with expanding our cluster, with not having to expand our cluster as usage grew. And of course, so when M7GD came out, we switched over. That was, a matter of changing a single digit in the config, plus doing a lot of performance testing. And what we found was that the local queries that were executing against NVMe SSD, that those started running about 20% faster when we switched from M6GD to M7GD. And if you remember what I said at the beginning, right, like, your pager's gone off, you're waiting for a honeycomb query to run, right? Like, every millisecond that we can save you is a time that your system is down for less because you're getting the answers faster. So this wasn't necessarily cost savings to us, but this was something that we felt was worth it to give our customers better query performance. But what if it's not enough speed to execute all of your queries locally, right? Like, Graviton processors, they can only run so fast per single machine. So what if we could throw tens of thousands of machines at this problem? Wouldn't that be nice? So the answer is yes. Because we're tiering older data onto S3 from our retriever indexing nodes, we're actually able to parallel process that data with AWS Lambda. So again, this is a thing where initially Lambda was only offered in the x86 configuration, but then Graviton 2 came out, and then support for Graviton 2 on Lambda came out. So the solution for our scaling problem of scanning, 60 days of data that no longer fits on the local SSD of one retriever node was to store the data on S3, use Lambda workers to retrieve the data, which makes this promise of less than 10-second query time work. So it also is the case that Lambda can be very expensive compared to running steady state on EC2. Our calculations say it's about 3 to 4 times as expensive for a comparable core running on EC2 versus Lambda. But the beauty is that we get perfect utilization, right? That we can pay by the millisecond for the Lambda that we're using. So when we switched over to using AWS Lambda with Graviton as opposed to x86 AWS Lambda, we found that we were able to substantially lower the cost of running those Lambda workers, because Lambda is something like 30 or 40% of our AWS bill. It's pretty substantial, but again, we believe it's worth it. This did not go perfectly smoothly initially, because, again, similar to what we encountered with Kafka, there were some hidden assembly dependencies. It's not that it didn't compile. Go makes it very easy to have a, if it's x86, execute this hand assembly. Otherwise, have the Go compiler do its magic. So it ran, but it actually ran pretty slowly. It actually ran about 10 to 20% slower than x86 Lambdas when we initially did our pilot. But we did some profiling, and we were able to determine which dependency needed its hand assembly updated. And then we were able to rerun the experiment, and we were able to see that better performance. We also had to do some capacity planning with the Lambda team, because when we turned up our Lambdas to 50% or 100%, we started to contend with ourselves, because at the time, the Graviton 2 Lambda shipments of Graviton 2 had not yet caught up to the same amount of capacity available in the x86 Lambda fleet. But by working with the AWS team, we were able to get sufficient capacity in place. We were able to optimize the bits of hand assembly that needed to be ported over to ARM. And also, the other interesting thing I'll point out here is you may be looking at this graph and saying, wait a second, the latency is the same, right? Like you're paying per CPU millisecond. So why am I saying that it was cheaper? Well, two things. Per core and per millisecond, Graviton 2 Lambda is about 10% cheaper than x86 Lambda. But also, if you look at the bottom of that slide there, you'll see that we allocated fewer vCPU. We allocated less memory per Lambda worker running on ARM compared to x86. And that turns out to be because our workload actually became network bound, that the amount of network available per Lambda worker to talk to S3 was our limiting factor. So if we squeezed the Lambda smaller because it was able to process more quickly per core, that we were able to get the same throughput and get charged less. So that's finally the point at which we began to see that 20 to 30% performance improvement for our Lambda bill. So since April of 2022, we have been 100% ARM servers in the serverful state. And for Lambda, we've been basically 100% Lambda. There's an asterisk there because we had encountered this problem with capacity on ARM Lambda. So we deliberately held back 1% of our Lambdas as x86 because we wanted to make sure that we didn't have the case of we needed to run an x86 Lambda due to a shortage of ARM Lambda. So we wanted to make sure that we're continuously validating, do the x86 Lambdas still work, even if it was potentially going to be worse for price performance. But about 2 months ago, I finally killed off all of the x86 Lambdas. And the reason was that we actually had an outage that was caused by the x86 Lambdas failing. And we decided at this point, like, we were comfortable enough with the capacity projections of the Lambda team that we're happy to run. So how do we become happy with the capacity projections? Well, it turns out when the Lambda team offers you double the concurrency for your ARM Lambdas, you say yes, and you say thank you, and then you say, OK, maybe I don't need to fail back to x86 anymore. So let me make that a little bit bigger and log scale maybe. So you can see basically that 1% holdback, that 1% of our traffic, that is log scale. That 1% of our traffic was running on x86. And then I took away the traffic entirely, and it was just health checks. And then finally, I just destroyed the Lambdas, and everything is 100% ARM now for our Lambdas. So in summary, AWS really enables us to go fast and be lean as a company, to have a lighter impact on the environment, to deliver better price performance, and to deliver faster results to our customers. And we didn't have to invest in doing this CPU research ourselves, right? The Annapurna team did all this research such that we can just increment a single digit in our AWS configs and get the benefit of everything that they're doing. So if we compare where we are today compared to 5 years ago, we're seeing about 2.2 times the price performance comparing the 8th gen M8G instances to the M5 instances that we were using before in 2019. We've scaled by a factor of 20 times over the past 5 years, but our AWS bill has only gone up by a factor of about 13x. And if you do the maths, that basically equates to about 1.6 times the cost efficiency per ingested trace. And that's because not 100% of our infrastructure is Graviton 4, right? Like because there still are the Lambdas, which are Graviton 2. There are still things like S3, which obviously are not directly impacted by the Graviton pricing. But overall, right, like I think that's a phenomenal outcome to be able to scale up the size of your ingest by 20x and not have your bill go up linearly at the same time. And we've seen, basically rock solid reliability, the same reliability as we were seeing before. In fact, maybe even better reliability because of that fact that the P99 is just so stable, as opposed to suddenly hitting an inflection point where your P99 gets worse if you're running too saturated. So if you're interested in more about this architecture and how we designed it and how we made it run in Graviton, I do have a book out. We're actually working on our 2nd edition now. The book is called Observability Engineering, and our work on our storage architecture is in chapter 16 on efficient data storage. So with that, go forth armed with this information, whether you're choosing to adopt Graviton or whether you're thinking about another kind of migration. Just remember, set some goals as to what you're trying to measure. Do the experiment, and then use the data from that experiment to make the business case to finish doing the migration, roll it out 100%, and then kind of drop that technical complexity of maintaining two things side by side. So if you're interested in talking to me after this, I'll be down here, or you can shout out a question live. And if this is something that you want to continue talking about, I'll be migrating to the Honeycomb booth after this, so you can feel free to talk with me about it there. So with that, that's what I have to share with you today. Also, I newly have joined Blue Sky, so I'm at lizthegray.com on Blue Sky, and I'm on LinkedIn. Thank you very much, and I look forward to taking your questions.